precipitation reactions, remember the solubility rules and know how to apply them. I've got a slide down here. If you remember, here's our solubility rules. You will have this chart on the final exam, so you can come look at it if you're wondering am I going to get a product that's going to be a solid or not. You can look at these solubility rules. Obviously, you see for anything that's got ammonium in it, NH4+, it will be soluble, no exceptions. Anything that has these main group 1 cations, lithium, sodium, or potassium, any compound with ammonium, lithium, sodium, potassium, these cations, they will be soluble, no exceptions. So you'll never get a precipitate if you have these cations in there. Then we have a whole bunch of anions. Anything that has a nitrate as the anion, soluble, no exceptions. It will not form a precipitate. Perchlorate, ClO4-, soluble, no exceptions. You will not get a precipitate if it's got perchlorate in the compound. Same with acetate, okay? These are all going to be soluble, no exceptions. We do have some exceptions with these 3 halogens. If these 3 halogens are the anion to any of these 3 cations, silver, mercury 2, or lead 2+, then you will have they'll be soluble unless they're combined with these. So if these are the cations, you will get a precipitate. Okay, if these are the cations and they're, so for example, AgCl, that would be a precipitate. Or if we had PbI2, lead iodide, these would be solid. Those would form a precipitate. But any other cation, then if the chloride, bromide, or iodides are your anion, it will be soluble. Same with sulfates. Unless sulfate is combined with these cations, it's soluble. So that means if I have barium sulfate, that is going to be a precipitate. Okay, or barium, lead 2 sulfate, or mercury sulfate, mercury 2 sulfate. So remember those solubility rules, know how to apply them. Lastly, we're going to walk through a couple of redox reactions, figuring out which element is oxidized right here and which element is reduced in the following reactions. You have to assign oxidation numbers, okay? If not, you're just guessing. So let's look at the rules for assigning oxidation numbers. These are right in your textbook. You can go review them. But here are the rules. Number 1, an atom in its elemental state will have an oxidation number of 0. So anytime you see H2, okay, hydrogen by itself, or any diatomic by itself, those are in its element. Anytime you see just a metal, sodium, okay, by itself, any element by itself will have an oxidation number of 0. Okay, that's very important. Number 2, a monatomic ion has an oxidation number equal to its charge. So for example, monatomic ion, that would be like chlorine, chloride actually, would have a -1 charge. As an anion, chlorides have a -1. So chloride, monatomic, mono meaning singular, it's by itself. If you had magnesium, okay, magnesium's main group 2, so its elemental charge as an ion would be a +2. Calcium, +2, okay? That's how we assign oxidation numbers for ions. Number 3, in a compound, an atom usually has the same oxidation number it would have if it were a monatomic ion. So let's say we have sodium chloride. Okay, here we would give sodium a +1 charge, oxidation number of a +1, and chloride would have an oxidation number of -1. If we had H2S in this compound, hydrogen as an ion will usually have a +1, so we'll give it an oxidation number of +1. And sulfur as an anion usually has a -2 charge, so we would give it an oxidation number of -2. That's what rule number 3 is saying. And then lastly, number 4, the sum of oxidation numbers in a neutral compound is 0. So for example, if we look at this compound we already wrote, H2S, we have 2 hydrogens. Each one we gave an oxidation number of +1. So total, that's +2. And just from the hydrogens. And then we have one sulfur, and we gave it an oxidation number of -2. So +2 -2 equals 0. Okay, sodium chloride, +1 -1 equals 0. Okay, So everything has to add up in a neutral compound to 0. All right, now that we know those things, let's go look at these redox reactions. All right, the first one, we have silicon Si. Notice it's by itself. What does rule number 1 say? An atom in its elemental state, meaning by itself, should have an oxidation number of 0. So we're going to give it an oxidation number of 0. And then we have chlorine. Okay, chlorine's a diatomic, so we wrote Cl2. It's by itself, so we give it an oxidation number of 0. Okay. On the product side, we have a compound. Chlorine, as a ion, usually carries a -1 charge, so we're going to give it the oxidation number that matches its charge as an ion. So we're going to give it an oxidation number of 1. And we have 4 of them. So if we have 4 of them, each one carries a -1 charge. Total, we have -4. We know that the oxidation numbers have to add up to 0, so silicon here has to be a +4 because we only have 1. So the oxidation number for chlorine was a -1. The oxidation number for silicon is a +4. So if you look at this, silicon goes from being 0 to being a +4 oxidation number. I have something on my screen. I'm trying to get it off. Sorry. Whoops. All right, and then chlorine goes from 0 to a -1. So now looking at this, we need to decide what is being oxidized, what is being reduced. Okay, if you apply oil rig, oxidation is the loss of electrons. When you lose electrons, you become more positive in charge. So that's silicon. So this is oxidized. And chlorine gained electrons because it went from 0 to -1. When you gain electrons, your charge is reduced, which is what happens to chlorine. So it's reduced. There you go. All right, let's look at the second one. We have chlorine. It's by itself, oxidation number of 0. We have sodium bromide. So we're going to give them oxidation numbers that they would have if they were ions. So sodium is a +1 oxidation number. Bromine is going to be a -1 oxidation number. On the product side, we have bromine by itself. That's an oxidation number of 0. And over here, sodium chloride, we have a compound. So we're going to give sodium the oxidation number it would have if it were an ion. So again, +1. Chlorine, usually as an anion, the only charge it ever has is a -1. So we're going to give it an oxidation number of -1. All right, so what's changing? We need to look for what's changing in charge. That's the key to figuring out redox. So chlorine goes from 0 to -1. Sodium is a +1 on both sides, so it does not change. So it's neither oxidized nor is it reduced. Bromine, however, starts out with a -1, and it, on the other side, on the product side, has an oxidation number of 0. So looking at this, what's oxidized, what's reduced? Chlorine is going from 0 to -1. It's reduced in charge. And bromine is going from -1 to 0. Its charge increases because it gave away electrons, so it's oxidized. Okay. If you also had to classify this reaction, it's redox, but if you had to classify it according to our 5 simple classifications, how would you classify it? Is it synthesis, decomposition, single or double displacement, or combustion? If you look at number 2 here, we have chlorine, sodium bromide, and then we have bromine and sodium chloride. If you notice, chlorine is replacing bromide. So this is single displacement. If you have to look at the first one, how would you classify it? Silicon and chlorine, 2 things by itself, coming together to make a compound. This is a combination or a synthesis reaction. All right, let's look at the last one. We have SbCl3 and Cl by itself. So this first compound, SbCl3, we're going to give chlorine an oxidation number the same as it would have as an ion. As an ion, we know it's an anion with a -1 charge, so we're going to give it an oxidation number with a -1. We have 3 of them, so -1 times 3 is -3. total. We know that this first element, Sb, is that, I think, antimony, has to have an oxidation number that's going to balance us out to 0. So it's got to have a +3 oxidation number. Okay, so +3 and -3 equals 0. Chlorine over here is by itself, so it gets an oxidation number of 0. On the product side, we have chlorine again in a compound, so we're going to give it an oxidation number of -1. But this time we have 5 of them, so -1 times 5 is a total magnitude of -5. So here, antimony, Sb, has to balance that to 0, so it's got to be a +5 because we only have 1. So now let's look at what is happening. We have chlorine in 2 places on the reactant side, and that doesn't matter. We just need to see what's changing in charge. So Sb, antimony, goes from being +3 to +5. Chlorine, some chlorine atoms are -1 on both sides, but other chlorine atoms, these chlorine atoms, go from 0 to -1. So antimony Sb goes from +3 to +5. It increases in charge. It must have given away electrons, so it's oxidized. And chlorine goes from 0 to -1. Its charge is reduced. Okay. So just another walkthrough on how to do redox.